Hey, welcome to Art of Code. My name is Martijn, and what you see here is a little scene that I came up with to demonstrate the effect of refraction. So in the last couple of videos we worked on reflection, which is obviously when a light ray hits the surface and it bounces off. And in the last few videos I showed how you could simulate that inside of a shader. Well, another thing that a photon can do is it can hit a surface and it can actually enter the surface, and then it will change direction and it will continue on its way. And with that you can make all kinds of cool things like this little gemstone over here. And so I thought I'd make a video about it. So if that interests you, you should definitely stick around. Okay, so this is where I am going to start. Let's call this Refraction. So this is my ray march starting template. The link is in the description if you want to follow along. If you want to know how to write a ray marcher, how to write basically a mini 3D engine inside of a shader, I made a video specifically about that. Go check that out. The link is also in the description. And just for all your newbies out there, it would be good if you've never done any shader programming. It would really be good to start really at the beginning. I made a video a couple of years ago called Shader Toy for Absolute Beginners. I highly recommend that, and not just if you're interested in Shader Toy, but just interested in writing shaders in general. Don't start here. This is going to be over your head probably. So start at that beginning video. Alright, so what are we going to do? So I have this standard ray marcher here with a little cube I can spin around. Let me collapse some functions that we're not going to look at. Yeah, I suppose that and that could be good. Alright, so the first thing that we are going to do is we are going to put in a background image. And for that I'm going to use a cube map. So I'm going to go to I channel 0, click on that, and then it's probably over here, so you click on cube maps and you pick which one you like. I like this one the best, but you can take any other one if you want. And then let's go down here to the main image, which is the main function of the shader. And then over here we set the color to black. Right? Color is vec3 of 0, 0, and 0 for the RGB. But here I'm going to say, okay, well, pick a texel out of this cube map. So I channel 0. Whoa! I guess I hit caps lock. Caps lock must be the most useless button on a keyboard. Like, when do you ever need all caps and lower caps when you use shift? I honestly take that button off the keyboard or use it for something better. Okay, I channel 0, and because we're looking taking a texel out of a cube map, we need a direction for that, and here we take the ray direction, which is where we are looking, right? And then I have to say .rgb in the end, because without this gives back a red, green, blue, and an alpha value, and over here we're only looking for a red, green, and a blue. So .rgb, or you could do .xyz if you wanted to. XYZ and RGB are interchangeable, so that means also over here, if you wanted to, you could say .rg. That wouldn't change anything either. Anyways, that's a little detour. Alright, so now we have the background here. And now what we would want is we would want to refract. Do I want to start with that? Well, let's just do a little recap here. So here we do the ray march, we get the distance, and then here we check if we actually hit the object, and then inside of that, inside of here we calculate the color of the object, right? And for that we get the 3D position where we hit, right? Let me just write it down. So 3D hit position, and then this is the normal of surface, okay, which is basically the direction, right? Just the orientation of the surface. And then here, well, we're not using this right now, but this is the reflected direction that we calculate. So if you followed my previous videos on reflection, then you kind of know what this is. So we take the ray direction that comes in from a certain direction, and it hits the surface, and then we use the normal of the surface, which is the vector sticking straight out of the surface, to calculate the reflected direction, right? And we can use that reflected direction to look something up from a texture. So let me get rid of the diffuse here, which we're not using right now, and let me calculate a reflected let me get the reflected color. So go here, reflex equals texture I channel 0 with not the RD like we did for the background. Although we could do that, and then it would just, let's just do that for shits and giggles and set that here, reflex. Okay, I have the same thing. I have to do .rgb over here. Okay, and then it will just disappear because it will render exactly the background. Okay, well, you could do kind of fun things like offsetting the background, stuff like that. But anyways, I'm digressing a lot in this video. Okay, so here we're taking the reflected direction, right? So now we have a reflection, and we can see that it's a reflection because if I look all the way down, I see the sky reflected. And if I look all the way up from underneath the cube, I see the floor, the ground reflected. So that's the reflection. Now, for glass or for anything transparent, we need not a reflection, we need a refraction. Okay, and luckily we have a function for that in GLSL called refract. And the refract function takes as an input the ray that you want to refract, the normal of the surface, and the last thing it takes is an index of refraction, and that's usually abbreviated IOR. And the index of refraction is basically a measure of how much the ray gets bent. Okay, so if the ray comes in and then it continues afterwards all the way like this, it has a certain index of refraction. But like for different materials, that how much it bends the ray differs for different materials. So the index of refraction is actually the ratio between the speed of light in a vacuum versus the speed of light in that medium. So like light goes through glass at a different speed than it goes through a vacuum, for instance, and through water it goes at a different speed from a vacuum and from glass. The index of refraction is a value that's always larger than 1, and the denser the object or the denser the material, the higher it is. For a vacuum, the index of refraction will be 1. For air, it's something like 1.01 because air is really not very dense. For water, it would be 1.33, something like that. For glass, it might be something like this. For diamond, it goes up all the way to 2.4 or something like that. All right, so that's the index of, let me just write that down, index of refraction. And you can Google that and learn a whole bunch of stuff about that. Okay, so so I'm calculating how the ray should continue after it hits the surface, right? So let's call this Refract. Kind of sucks that reflect and refract are so close together. It kind of screws with my naming of variables. Alright, so that is the refracted direction. So let's use that instead of the reflected direction. So Refract. Let's see what that looks like. Oh yeah, and then there's one other thing. So yeah, so this looks kind of weird, right? You see here where it kind of bends stuff weirdly, and most of it is gray. This took me a while to figure out. If you go from a less dense medium to a more dense medium, so like in this case, we're going the light ray goes from the air into, let's say, glass. Okay, so it goes from less dense to more dense. Well, if you do that, then you need to actually use the inverse of the index of refraction. So the inverse would be 1 divided by the index of refraction. So now that already looks a lot better. Like it looks a lot like the reflection, right? But it's not reflection, because if I look up now, I actually do see the sky, and if I look down, I do see the ground. So that's how you can distinguish those, even though at first sight it kind of looks like it does the same thing. Still doesn't look very convincing though for a piece of glass, and the reason why is because if you actually had a real block of glass, well, the light ray refracts when it enters the object, right? But it also refracts again when it exits the object, and we did not simulate that exit yet. So let's try to do that. And so what we have to do is, so here we ray march the outside, right? So outside of object. But like now over here we have to continue the ray march inside the object. So let me just copy this here. Over there. And I can call this D in for the inside of the object. And then give some space here. And then the ray march has to start where we hit the surface, right? And where we hit the surface is over here, right, at point P. And then we have to go in the direction of the refraction, right? So over there. Now there's a few issues with this. The first issue is that when we start ray marching at this point P, well, this point P came out of the first time we were in the ray march loop. And let's just look at it real quick here. So here's the ray march loop, and so the first time it starts ray marching from the camera, step, 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 closer. It's closer and closer to the surface, and at some point it gets so close to the surface that this becomes true here, that the distance of the surface is smaller than some very small value, and then it says, okay, we hit the surface, and it breaks out of the loop. But if we use that same point and we throw that right back into the ray march, well, then the first time we get in here, it's going to kick us out of the loop right away. So that doesn't work. And this is exactly the same as what we had for the reflection. And with the reflection, when we came in here, like I moved the point just up a little bit, just away from the surface. But because now we are marching into the object, we have to do the opposite. So we have to take the point and push it down a little bit. And so let's do that. Yeah, and actually over here, so over here, let's make a variable and call it P enter, which is the position where we're entering. Okay, which is just P minus, in this case now, the normal times the surf distance, and then times some fudge factor to make it a little bit bigger to make it work. So before, for the reflection, because we always were on the outside of the object, I did plus, but now we are inside of the object. Okay, and so here we say D enter. Okay, so now we want to ray march on the inside of the object. Now, there's another issue, which is that if we go over here, so the ray march tests the distance to the object at each step. And the distance is calculated over here, right? And the distance is positive for anywhere outside of the object, but as soon as you get in, well, and then it goes all the way to 0, right? So 0 is the surface of the object. And then when we're, for any 3D position inside of the object, it's actually negative. And we can't really ray march with those negative values. So what we would have to do on the inside of the object, we'd have to invert. We'd have to invert the distance function. We'd have to make it, and by invert I mean just make it minus, so that now for any point inside of the box it's positive, and for any point outside it's negative. And so, but we need it only inverted when we're inside of the object. And so this is how I'm going to do that. I am going to add to my RayMarch function over here. I'm going to add a float, and I'll call it side. And side is a float that can either be +1 or -1. And when I render the outside, I'm gonna call it with +1. So now, if I multiply this over here, I just get my distance times 1, which is my distance. And for the inside, I'm going to enter -1, so it's going to be my distance times -1, so it's going to be inverted. So if we over here we're RayMarching the outside, well then over here I have to say comma 1, and for the inside over here I'm going to say comma -1 to RayMarch the inside. So this is inside the object. Now we're inside the object, and now we can do the same thing as what we did over here. So we don't have to do this if here, because once we're inside the object and we keep marching, we are always going to hit the object, right? Because at some point we're going to have to exit the object. So we don't have to do this. And so we can get directly to this. So let me copy this here. Yeah, something like that. Copy that. And so here, this is the exit point, right? So exit. So 3D position of exit. And the exit point is, well, it's similar to over here, but we have to fill in different things, right? So we have to say, this is P enter now. So the ray origin is P enter. And the direction that we march in was the refracted direction. And the distance that we march is this, right? Okay, so now we calculated the exit point, and now we can just calculate the exit normal, which is get normal of P exit. But for our calculations, we need, because we're inside the object, we need the normal to be flipped. So I'm going to just put a minus there. Yeah, let me just take that out. Alright, so now we have the exit point and the normal at the exit, and so now we have to calculate another refract, because like now it's inside the object and now we're going to go back out, and so now we have to refract the light ray again. So I can just copy this. Okay, and yeah, I'm going to have to rename these a little bit. Let me just say, so instead of ref dir, I'll call it ray direction in. So this is the ray direction when we go into the surface. Ray dir when entering. And now I'm going to calculate an RD out. Okay, so go over here and call it RD out. And RD out is RD in, is the ray direction when you enter the surface with the exit normal. And then now, because we are inside of the object, so now we're going from high density medium to a low density medium, right? We're going from glass to air. Well, now we do have to take just the index of refraction. So again, if you go from a low density medium to a high density, so if you go from air to water, or from air to diamond, or from air to whatever else you have, you actually have to take the inverse. But when you exit it, you have to take the actual index of refraction. And so now we have the RD out, and now we can use that to get the refracted color. So let me, yeah, let's just use this for now. Okay, that's not going to work. Refer dir, because that's called RD in right now. And RD in. Okay, so now we have this. And that doesn't look terribly correct. And that is because there is the concept of total internal reflection. If you go from a high density medium to a low density medium, then, so if I'm inside of the glass and I want to go out of the glass, what happens a lot is, like, if the ray is at a grazing angle, it comes in onto the surface, then there is an angle at which all the light actually gets reflected, so none of the light actually goes through. And that's called total internal reflection. And this refract function, when it gets to total internal reflection, it doesn't output a proper ray direction anymore, and it just sets all the values to 0. And so we have to detect if all the values are 0, and then we have to actually do a reflection instead. And so let's do that. So over here, I'm going to say if RD out. So I could say if RDR.x equals 0 and RDOut.y equals 0 and z equals 0. I could do that. It's just a cumbersome way to write it. And so a faster way to write it would be just if length RDOut, RDOut equals 0, then we have to reflect instead of refract. So then RDOut equals reflect of, reflect. So then we just have to reflect the ray, and we reflect it by taking the ray direction, which is RD in, with the normal, which is n, the exit normal, right, like that. And so that will give me something like this. And that, my friends, is proper refraction. All right, so now over here, this says length. So a length is basically Pythagoras, right? Just x squared plus y squared plus z squared, and then the square root of that. We don't need that square root in the end, and so we can also, like a nicer way to write this that comes down to the same thing is to take the dot product with itself. So if I do dot product, dot RDOut and RDOut, that gives me the exact same result, but we don't have the square root, which is better. So this is basically just RDOut.x times RDOut.x plus RDOut.y times RDOut.y and the z and the z. And so that comes down to the same thing. That's only going to be 0 if the x, y, and the z are all 0. Okay. Yeah. So for now, I'm going to leave it here. In the next video, we're going to make this into a beautiful gemstone. So if you don't want to miss that, be sure to like and subscribe and comment. And also, I asked before, if you make anything cool and you want it showcased, let me know, and maybe I can show it, like the ones that I'm showing right now. And either way, I will see you next time.